In this section, 5.2, diagonalization, they start with similar triangles and similar matrices, and they have this definition that I want to elaborate on. Let A and B be square matrices, the number of rows equal the number of columns. Then we say that B and A are similar if there is an invertible vector P such that you could write B as this vector P inverse times P multiplied by A, in that order. Now, we really don't need all of those. We just, really quick, the determinant of similar matrices are the same. So both of those have the same determinant. If A is invertible, then P inverse A inverse is invertible. If A is invertible, then P inverse AP is invertible. And the nullity and the trace, all of these properties that you can get out of that. We want to use just the first couple in this section, and we're going to come back to similar and go about it a different way. Now I want to elaborate on this really quick. Actually, I'll elaborate on the next theorem. A square matrix is said to be diagonalizable. That means you could write it as a diagonal matrix where the diagonal entries are non-zeros and everything else is zero. If it is similar to some diagonal matrix, that is, there exists an invertible matrix P such that P inverse AP is diagonal. In this case, the matrix P is said to diagonalize A. So this is what's going to happen. We're going to be given A. We're going to take A and we're going to write it as where this is a diagonal matrix. I'll talk about P in a minute, and this is the inverse of P. And we're going to take A and set it equal to that. That's really what we're going to do. And I'll elaborate on that once we get there. How do you find P, how do you find D, and why is that significant? And if you have an n by n matrix, the following statements are equivalent. A is diagonalizable, and A has n linearly independent eigenvectors. So if A is diagonalizable, then you have this case is true. Those are equivalent. If this is not true, then this is not true. And the last theorem, if k is a positive integer, so k is just a number that's positive. It's an integer that's positive. Lambda is an eigenvector of matrix A, and x is the corresponding eigenvector for this lambda of A. Then, if you take a to the k, then x to the k is an eigenvector of a to the k, and x is the corresponding eigenvector. Actually, let's keep it as that. Now, I'll elaborate on this definition in a minute, and I'll tell you what all of that means. In those first two problems, they say, show that A and B are not similar. Well, for them to be similar, you have all of these things to check. Any one of them that doesn't work, you're done. I'll go for the first. I'll find the determinant of A. That is 16 plus 2, which is 18. And I'll take the determinant of B. That is 16 minus 2, which is 14. Since those are not equal, those are not similar. And the same deal here. If I take A, probably the best way to do this. Oh, not even. Determinant of A, I was going to say you could use a shortcut, but if you have a 0 row or column, what does that mean? Pick that row, and that determinant is 0. While when you go here, If I pick this row, that is 1 times 2, oh, that is, let me just double check really quick. That is 0, that didn't work. Okay, what else can I check? The second case, it says determinant. If A is invertible, hard to find. Rank, okay. Those two must have the same rank. So what's the rank of A? If I take -2 row 1 plus row 2 in row 2, and if I take -3 row 1 plus row 3 in row 3, I'll get 1 0 1 0 0 0 0 0 0. Set that equal to 0 0 0. The rank of A would be 1. Versus here, if I take negative row 1 plus row 2 in row 2, and if I take row 1 switch with R2, no, row 2 switch with R3, the rank of B is 2, not similar. Now, only one of those have to disagree. Again, not a big deal. If you're not seeing the similar for this section, we'll come back to it. Let's talk about this. Find a matrix P that diagonalize A. What do they want? They want to take A and write and check by computing your work. Now I'll show you how this works. We want to find a matrix P such that I could take A and write it as P, a diagonal matrix, and P inverse. Now, if I solve this, if I multiply by P inverse on the left and P on the right, do you agree that a matrix times its inverse is the identity? And that's what we're talking about. And I'll give you a hint. I'll show you what those are. This diagonal matrix, if it's a 2 by 2, will be the eigenvalues, and P will be the corresponding eigenvectors. So let's start. We find the determinant. That's how we're going to find B. P, determinant of lambda I minus A would be equal to 0. So we're going to find the eigenvalues and eigenvectors. That's going to be lambda plus 14, negative 12, 20, and lambda minus 17 equal to 0. So that would be, and those numbers are not very pretty, lambda plus 14 into lambda minus 17 minus plus 240 equaling 0. ولا عن جد يمكن مش حاش ولا هذا اللي طلع معطن خد لك من عمل الخمسة يعني مشحر الحكي. and that will be lambda squared minus 3 lambda plus minus 14 times 17 238 plus 240. That's simply lambda squared minus 3 lambda plus 2 equal to 0. So lambda minus 2, lambda minus 1. So I got lambda to be 2 or 1. Okay, very good. Now, I'm going to take lambda equal to and throw it in there. I'm looking at 16, negative 12, 20, and negative 15. I could take row 1 divided by 4, put it back in row 1. Take row 2 divided by 5, put it back in row 2. 4, negative 3, 0. 4, negative 3, 0. And obviously, if I take negative row 1 plus row 2 in row 2, I'll get, so my conclusion, for lambda equal 1, the lambda equal 2, I'll get x2 to be free, and x1 to be 3/4 x2. Again, they clear the fractions, so they multiply by 4, make that a 3, and that's a 4. Now I take lambda equal 1, and I do the same thing. 15, negative 12, 20, negative 16, 0, 0. Here, take row 1 divided by 3, put it back in row 1. Take row 2 divided by 4, put it back in row 2. And what would happen? You'll get 5, negative 4, 0, and a 5, negative 4, 0, and obviously take negative row 1 plus row 2 in row 2. So if I say x2 is free, then x1 is 4/5 x2. So for lambda equal 1, I'm getting the vector multiplied by 5. So if you let this be 5, that'll be 4. Now, I'm going to take A. They want me to write P inverse AP. Let me show you. I have two options to do, and you could do either one. It doesn't matter. I'm going to take lambda equal 2 yielded 3, 4, and lambda equal 1 yielded 4, 5. I could go on the side and say A equal P D P inverse. Well, what's A? What's P? The order, you could write those anywhere you want, but you gotta make the order match. If you put this vector first, then the lambda associated with that comes first. If you put this next, you could switch those if you like. Put the 1 there and the 2 there as long as you switch those. All what I have to do now is find the inverse of P, and I know how to do that. If this is P, the inverse of P will be 1 over the determinant. 15 minus 16 is -1. The diagonals, and multiply the non-diagonals by a negative. Since that's a minus, that's -5 for -3. But they're asking us to do find P that diagonal is A. P inverse A inverse. Well, we're claiming that P inverse is right there. So if I take P inverse A and P, and as I showed, if you take P inverse AP, you'll get the diagonal matrix with the eigenvalues. Notice there's P inverse, there's A. I should get the eigenvalues, which is the diagonal matrix, and let's see. But here you have to multiply those 3. And let me show you really quick. If I multiply those two, that would be 5 times 50, 70. 70, positive 70, minus 80. That's 10, negative. And that'll be -60, -60 plus 6, that's an 8, I think. I'll double check the numbers. Negative 14, 4 times 14, 40. -56 plus 60. And 48 minus 51. 48 minus 51. I think that's a -3. And what would that be? 30? No. -30 plus 32. -40 plus 40 for the bottom. 12 minus 12. And 16 minus 15. And it's not a big surprise. Oops. And if you were to choose in P, if you were to choose to put this first, then you would have gone the inverse associated with that. Those would have swapped. Now, what do you have to do? All what I want you to do is find this vector P and find its inverse. You could write this, that's fine with me. You could write this, that's fine with me. But when we use it, we're going to use this. And I'll show you what that means. We want to do that for a 3 by 3, which is a bit more work, a bit annoying, but it's okay. Good practice. Okay, so if I take the determinant of A minus lambda of lambda I minus A, if I pick this row, I will simply get lambda minus 1 times lambda minus 1 squared minus 1 equals 0. Or simply lambda minus 1, this is the difference of squares, that's lambda minus 1 minus 1 into lambda minus 1 plus 1. So that's lambda minus 1 into lambda minus 2 into lambda equals 0. Lambda equals 0, 1 or 2. Lambda equals 0. I take negative row 2 plus row 3 and row 3, that means x3 is free, x2 equal negative x3, and x1 is 0. So for lambda equals 0, I'm getting 0, negative 1, 1. For lambda equal 1, put that in that matrix, and I'll get 0, 0, 0, 0, 0, negative 1, 0, negative 1, 0. What does that mean? Well, if I put them in order, if I take, no matter how I put them, that's x2, x3. x2 is 0, x3 is 0, x1 is free. So that gives me the vector 1, 0, 0. And if I let lambda equal 2, was it 2? 2. Then I'm looking at 1, 0, 0, 0, 1, and 0, negative 1, 1. And if I take negative row 2 plus row 3 and row 3, I'll get x3 to be free, x2 is x3, and x1 is 0. P would be excuse me, and there it is. Now the problem on your homework, P works out to be very nice. Finding the P inverse of this, you know how that works. That's going to be a bit of work. You can list 1, 0, 0, 0, 1, 0, 0, 0, 1 and do your work until you get the identity on the left, and that will be your P inverse. The problem on the homework works out very nice. It's one step and you get the inverse. So you could, just to cut on time, that's how it works. And we could take A and write it as P dP inverse. Or if you take P inverse AP, you will get D. D is the diagonal with the identities in that order if you listed P in that order. Now, and here we are. Find the geometric and algebraic multiplicity of each eigenvalue of the matrix A and determine whether A is diagonalizable or not. If A is diagonalizable, then find the matrix P that diagonalizes A. Just find P, you don't have to find the rest. Well, if I look at 14, if I take the determinant of lambda I minus A and set it equal to 0, I'm looking at lambda minus 5 or I could simply see that this is diagonal, so what's lambda? Now we have a problem. If I substitute lambda equal 5 in there, the most I can get is 2 vectors. I need them to be 3, right? So the geometric multiplicity here is that I have lambda equal 5. right? Lambda minus 5 cubed. So I'm only getting one vector. There's no way of getting three vectors out of that, right? And if I write it out, I'll show you just in case you're wondering. That's 0, 0, 0, negative 1, 0, 0, and 0, negative 1, 0. In this case, I notice that x1 is 0, x2 is 0, x3 is 3. Well, I only got one vector. How am I going to write P in terms of one vector? That doesn't work, right? P needs three independent vectors. If I only have one lambda, I can get at most two zeros because this is multiplicity 3, right? So I could get one or two or three vectors, but I know for a fact from the matrix manipulation, the best I could do is 0 or 2 of those, which means I can get two vectors, not three. So this is not diagonalizable. Diagonalizable. I need an n by n to be able to find the inverse, right? This is 3 by 1. I got 16, another elaborating on what we just said. Characteristic equation has to do with polynomials from college algebra or pre-calculus, wherever you saw this. This is the characteristic equation of a matrix A is given. Find the size of the matrix and the possible dimensions of its eigenspace. Well, let's start. I'm looking at this and I notice this is 5 by 5 to get those eigenvalues. I see that lambda equals 0, which indicate the possible dimensions would be 1, 2, or 3. Those would be the possible dimensions of eigenspace. And why is that? Because the multiplicity is 3. Here, I see a quadratic. Well, that factors lambda minus 3 into lambda minus, no, not adding, minus 6 lambda plus 1. So lambda equals 6 has multiplicity 1. So the dimensions of the eigenspace must equal 1, and lambda equal negative 2, the same deal. It's not negative 2, it's negative 1 here. Let me factor that properly. Lambda minus 6 and lambda plus 1. So that's kind of like when you have powers of polynomial and you were thinking how many zeros can they have. How about here? Lambda minus, so the only possible factors are 1. If I take 1, 1, negative 3, 3, and negative 1, plus or minus 1, 3, okay, that works. 1, 1, negative 2, negative 2, 1, 1, 0. That is lambda squared minus 2 lambda plus 1. That's lambda minus 1 squared times lambda minus 1. So here I have lambda minus 1 cubed equals 0. So lambda equal 1 could have 1, 2, or 3. Those could be the dimensions of the eigenspace. And if you recall back in the days, 1, 0, 2 zeros, or 3 zeros. Back when we did polynomials. Now, the main use of this whole process is figuring out what is 8 to the 100. And in case you're not sure, A to the 100 means you're going to multiply the matrix by itself 100 times. But notice what happened. If I can take A and write it as P D P inverse, A to the 100 would be P D P inverse 100 times. But isn't that I? And wouldn't that P D D D D and P inverse? And what happened when you multiply a diagonal matrix by itself 100 times? If I had a diagonal matrix that was on your previous exam, if I raise that to the 10, that's simply raising those to the 10. That was on exam 1. So instead of multiplying a matrix by itself 100 times, all what I have to do is find the eigenvalues, the eigenvectors associated with that, find the inverse, raise this to the 100 and multiply that. So I'm multiplying 3 matrices instead of 100 of them. Here, they want me to find A to the 10. I could multiply A by itself 10 times. Or I could say, let me check. If I take this A and write it as a diagonal matrix. So, what is the determinant of lambda I minus A equal 0? That is lambda minus 1, 0, 1, lambda minus 2 equals 0. So that's lambda minus 1 times lambda minus 2 equals 0. Lambda equal 1 and 2. I already got the diagonal matrix. Now, if it's up to you, you could start with lambda equal 1. You could start with lambda equal 2. It makes no difference. If I start with lambda equal 1, that's 0, 0, 1, 1. So x2 is free, and x1 is negative x2. So with lambda equal 1, I'm getting the vector negative 1, 1. With lambda equal 2, I'm getting 1, 0, 1, 0. If I take negative row 1 plus row 2 and row 2, I know that x2 is free and x1 is 0. With lambda equal 2, I'm getting 0, 1 as the corresponding vector. Now, I'll give you two options. Either you say P equals negative 1, 1, 0, 1. And if you did that, then you are saying that D equal, it has to go in order. If you put this vector first, you must put that entry first. And if you put that vector next, you must put 1 there. Or you could say, forget that. I want 0, 1, negative 1, 1. You could do that too. In that case, D would be, I meant 2. In that case, you swap the order. That would be the 2, that would be the 1, and that's the only catch. So, once I figure this out, it's up to you how you want to do this. I could say I'm going to go with the first. I'm going to say take this vector, take this matrix A. I'm going to write A as I did mention that, right? Yeah. I'm going to write A as P. P is negative 1, 0, 1, 1. D. And the inverse of this. In this case, P inverse will be 1 over the determinant. That's 1 over 1. Swap those and multiply those by a minus. And I could show you that this works really quick if I take those and I multiply them out. When I multiply the first two, I'll get a 2 by 2. I'll get negative 1, 0, 1, 2, multiplied by this, 1, 0, negative 1, negative 1. That would be negative 1, that didn't work. Let me double check really quick. Make sure I got this right. 1, 0, negative. So 1 over the determinant, 1 over the determinant, check. Okay, not to worry, I found the mistake. It's right there. When I put lambda equal 1, 0, 1, 1, 1 minus 2 is negative 1. So if x2 is free, x1 would be positive x2. So that's a positive. If I fix that, so if we choose the first, 1 over the determinant, okay, 1 over 1, swap those and multiply the non-diagonal by a negative 1. That's perfect. So that will be P positive 1, 1, and here we have a positive 1. There we go. If I put a positive there and a positive there, let's see what happened now. If I multiplied, and I was working this out. Let's do this again, one more time. If I multiply those two first, I'll get 1 plus 0, that's 1. 0 plus 0 is 0. 1 plus 0 is 1, and 0 plus 2 is 2. And if I multiply that by 1, 0, negative 1, 1, I'll get 1 minus 1 plus 0, which is 1. 0 plus 0 is 0. I'll get 1 minus 2, which is negative 1, and 0 plus 2, which is 2. That should be A. It is. There you go. Now what? Now you say, look, if I want to take this to the 100, then that's to the 100, then that's to the 100. But we know what's going to happen when you're going to list them out. When you list those out to the 100, everything in between is going to vanish. The only thing that's going to be left is 1, 0, 1, 1 times 1 to the 100, 0, 0, 2 to the 100. Again, if you're not sure how I'm getting that, it's on your first test. And now all what you have to do, instead of multiply the matrix by itself 10 times or 100 times, or this 10 power, not 100. The problem says to the 10. I got excited. And what will happen? That would simply be 1, 0, 1, 2 to the 10, multiplied by 1, 0, negative 1, 1. And that would be 1, 0, 1 minus 2 to the 10, and 2 to the 10. Right? So 1, 0, negative 1, 2 to the 10th. If you multiply that by itself 10 times, remember you can't, that would be simply 1, 0. What is 2 to the 10th power? You could leave it like that, of course, but I just want to show you what it is. If I take 2 raised to the 10th power, 1024. And 1 minus 1024 is 1023. And that's pretty much the main use, and it's a really big deal of how to use eigenvalues and eigenvectors, and in class I'll mention that, why is that, and elaborate on that.